Welcome to Speaker Night at the David Dunlap Observatory online with the Royal Astronomical Society of Canada, Toronto Centre. My name is Denise Chilton, and I am the RASC Toronto Centre DDO Committee Chair and an operator of the 74-inch telescope at the David Dunlap Observatory. Together with our outreach coordinator, Quentin Wayrich, I am delighted to be your host for tonight's lecture. I'm also very excited to welcome you, our viewers, to tonight's lecture. If you haven't already, please take a moment to say hi in the YouTube chat and tell us where you're joining us from. I've heard there are several people from across the country and even across the continent online with us tonight. Welcome. The Royal Astronomical Society of Canada's mission is to enhance understanding of and inspire curiosity about the universe through public outreach, education, and support for astronomical research. In partnership with the City of Richmond Hill, RASC hosts outreach activities at the David Dunlap Observatory, or DDO. The observatory is home to Canada's largest optical telescope. While we miss welcoming guests to the DDO facility, we are happy to bring you virtual programming instead throughout this pandemic. We would like to start by acknowledging that the David Dunlap Observatory in Richmond Hill stands on the traditional territories of the Wendat, the Haudenosaunee, and the Anishinaabe peoples, whose presence here continues to this day. We would also like to acknowledge this land is at the meeting place of two treaties, the lands of the Mississaugas of the Credit and those of the First Nations of the Williams Treaty. We thank them and other Indigenous people for sharing this land with us. Tonight, it's my great pleasure to introduce our speaker, Dr. Saeed Rastgoo. Dr. Rastgoo was born in Iran and studied his undergraduate and MSc degrees there. He then moved to Uruguay to study his PhD in quantum gravity under the supervision of one of the pioneers of loop quantum gravity, Professor Rodolfo Gambini. This was followed by two postdocs in Mexico, one in UNAM and the other at the Universidad Autónoma Metropolitana. After that, he became an assistant professor at the Monterrey Institute of Technology in Mexico in mid-2018. In 2020, Dr. Rastgoo moved to Canada and became an assistant professor at York University. His current research is particularly concentrated on the black hole interior, its dynamics, and its singularity. He also does research on the fundamental nature of space and time and studies how we can obtain information about their hidden secrets by analyzing the behavior of gravitational waves and gamma rays coming from far away astronomical objects. Tonight, Dr. Rastgoo will discuss black holes, what we see on the outside and what happens inside. If you have questions for our speaker, please post them in the YouTube chat. Saeed will have time to take your questions at the end of his talk. Please join me now in welcoming Dr. Saeed Rastgoo.
Thank you very much for the nice introduction, and thank you for having me. I'm very happy to be here tonight, the Royal Astronomical Society of Canada, and talk about black holes, and I'm very happy to discuss that after this, if there are any questions. So as you mentioned, my work is about black holes and what we call quantum gravity. And tonight I want to talk to you about some of the aspects of the black holes that we see from the outside and some of the guesses or educated guesses, if you want, based on calculations in physics and math, what happens in the interior of the black hole. So let me actually start by telling you something that you probably know, but just to make everything clear about the universe. The universe is actually, if you look around you, you see that the universe consists of, essentially you can describe it as a bunch of objects interacting with each other over the arena of space and in time. So they're interacting in time. Now you can see all of these interactions, boats in the sea, water hitting them, or billiard balls, or clouds, for example, in the sky moving around and hitting here is a bridge, and all of these are interacting. Now, what I mean by objects here, all of these things that you see here, in physics we call them matter, and the matter, as you see, there are these consists of, for example, electron, protons, and other particles. Now, the interaction is done by forces that these particles exert among themselves. And these forces, not long time ago actually, that there are 4 of these forces. One of them is electromagnetism. Basically, any particle that has an electromagnetic charge exerts a force on another particle. Here you see the clouds are moving around. That's because actually there's electromagnetic force between them. The friction force is electromagnetic in its foundation, and almost everything you see around you is affected by electromagnetism. Then you have weak nuclear force, and that's the force that you don't see really around you, but that's responsible for nuclear decay. You can see its applications, important applications in medical physics, in imaging. And then you have the strongest of all, which is called the strong nuclear force. By the way, weak nuclear force is called weak, but it's only weaker than a strong. It's not weaker than electromagnetism. So it's the second strongest force. Then the strong nuclear force is actually very strong. And the reason is that if you think about the nucleus of the atoms, there are a bunch of protons and neutrons sitting there, and neutrons don't have any charge, but protons are positively charged. So all of them are together in that small space. And so the question is that how they are not repelled from each other by electromagnetic force? The answer is that because there is a attractive, strong force that is binding them together. So that's how strong it is, the strong nuclear force. And finally, the subject of today's talk, gravity. And gravity is the weakest of all, but actually the most mysterious of all. We will see later. Then the space and time, actually we found that so it's the background, everything is moving around and interacting on. We found out that actually space-time is like a grid. And you can think of it as a grid, and I will talk about that in more detail. But after some more investigation about the nature of these forces, we found out that gravity is actually not a force. Gravity is actually a space-time itself. So it's the curvature of a space-time. So we really, modern physics remove gravity as a force and puts it in as the background. So you have actually 3 forces here, or 3 in physics, they call them fields of force, and they're propagating and acting on another field of force, which is called gravity, which is actually equivalent to a space-time. So a space-time is nothing, or actually gravity is nothing except the curvature of a space-time. To see that in more detail, let's now get to more specialized part of the talk about the classical gravity and space-time. So by classical, we mean that something that is not quantum mechanical at the moment. So it's really none of those awkward effects of quantum physics are present there. We will get there in this talk at the end. But so essentially, you see this is a space-time. You can see a grid here. And if you put a material object at the center, you see that it curves a space-time. So the manifestation of that that you see in your real life is that object absorbs things, so that you think of it as a force, but it's really because the space-time is curved, not only a space, but also time. And I will talk about that later in the black holes. But then that leads to the curvature, to the feeling that we have. So if the objects move around, then the curvature is moving around. So that's what happens if planets are around, and so on and so forth. And you can see these awkward effects because of the curvature of space-time. So you have here sun, and you have a bunch of galaxies here. It doesn't matter. So if the light passes close to them, and in this case, light passes close to these, the light bends, so curves, and that's not because the light has any mass, right? So the force of gravity, you usually assign it to a mass, but light doesn't have any mass. But the reason that it bends because of gravity is that gravity is the curvature of a space-time. Okay. Now let's go to an example. So you see that you can think of gravity, how it gives you the feeling of an attractive force in this experiment. So this is an elastic sheet here. Think of that as a space or a space-time. We put a ball here. This is a planet or sun, and we release another object, another planet or another star around it. And you see that because of the curvature, this goes around the central object. It's only because of the curvature. If there was no curvature in the center, the object would just start and go on a straight line, and you wouldn't see any rotation around the central object. So this is a simple way that you can see that how this sheet is curved, and this sheet is represented as a spacetime represented by this sheet. Okay, so one of the really interesting things that you can see because of the curvature of spacetime, as I also mentioned before, is the gravitational lensing. So you see that there is an object here. The light comes towards us, but actually this light, you see that it should actually go this way, and we should not see it. But actually, because something between us and that object, some galaxy or some massive object, it curves the spacetime, then the light comes back to us, and also it comes from below, from right, from left. And instead of seeing one point, you see, so this is the central object, and instead of one point source, you see a circle around it because the light's coming from right, left, up, down, all of the angles. You can see the same effect actually here. If you have a glass, like the bottom of the glass, if you put it on a paper, you can see this. And this also happens in black holes that we'll see in a moment. So these are all the magics of gravity and the curvature of space-time. Now let's get to the black holes. And from many of the documentaries you have seen, you know what black holes are actually. But let me just give you a little more rigorous definition. A black hole is a trapped region in a space-time. By trapped region, I mean the geometry of a space-time is such that nothing can escape from the interior of that region, right? So this is only possible if you have a space-time together. If you just separate a space and time, and just a space itself cannot have these properties. But so you can see these more clearly mathematics. But anyway, so that's the definition of a black hole. So you can see that definition of black hole has nothing to do with singularity, essentially. So it's just a trapped region. But it turns out that every black hole have a singularity. So this is the cartoonish representation of a black hole. So you have a shuttle, just ride on it, go inside the black hole, and that's it. Your fate is doomed. You can never go back again. So that's you stay in the interior of the black hole. So black holes have some properties. One of them is that based on theorems by Penrose and Hawking, Penrose won the Nobel Prize just recently because of this. They all have singularity, something called singularity inside them. And singularity is a place or a region in a space and time where you have infinite curvature. And by infinite, we mean that some number there, the curvature of a space-time becomes infinity. And whenever you have infinity, it means that your theory breaks down. You cannot do computations with infinity because it's not a number, really. It's a concept. So infinity plus 1, again, is infinity. So it's not like other numbers. So it signals that your theory, which is a theory of general relativity, breaks down at that point. And you need another theory, which we call quantum gravity. I will talk about it briefly later. The other property is called the horizon or event horizon. And it's the boundary of that trapped region. So that's called the event horizon. And the distance from the event horizon to the singularity or the center of the black holes, in case of a special type of black hole that is not rotating and doesn't have charge, etc., it's called the Schwarzschild black hole. So the distance is called Schwarzschild radius. And this is written as R index S. Okay, so we have this concept of black hole. Now let's go to see what happens in the exterior, outside of the black hole, and what we can see. So recently, the Event Horizon Telescope took a picture of a black hole, and the picture was this. At first sight, it doesn't look that much. It's like a blob of light with something dark in the center. And just don't think that this picture was taken just with one shot and that's it. So it was of 1 or 2 years of work of removing noise and all. It's a really hard work to do. But anyway, so this is the picture, and what you see in the center, you might think that this is the event horizon or the black hole itself. So the black hole is actually defined by that horizon, but it's actually not. It's called the shadow of a black hole, what you see there, and I will explain what the shadow of a black hole is. Before that, let me tell you what if you go close to a black hole, what you see. So a black hole, this central object, this is the event horizon, the black thing here. And usually you have some material object, some matter going around this black hole, rotating and then falling in. And that's called the accretion disk. And this is a really, really hot plasma, going around. And plasma means like basically very hot gas. It's very hot because it's rotating at speeds very close to the speed of light, and that makes it hot. And they hit each other, these particles, and they become hotter and hotter. And some of that matter is actually kind of spit out of the top of the black hole. It does not come from the inside of the black hole. Nothing comes out of the inside of the black hole. So it just moves from from very close to the black hole, goes up. And these jets are very strong. They actually, their length sometimes is like 4 or 5 times the length of the whole galaxy. So you can see the speed and the power of these these jets that is coming from the energy of the black hole. Okay, so now take the black hole. And now this is the event horizon of the black hole, as I mentioned before, the boundary of the no return, basically the no return boundary. And if you look at the black hole from the from somewhere close to the black hole, you will see that accretion disk. This is the gray area. That's the material part that is rotating around the black hole near the speed of light. But you see actually 2 other structures here. So you have this empty space here, and you have this. Actually, this is a sphere. It's not just a ring. It's not a circle. It's a sphere, but we have drawn this like here because you can see the interior of that. So you have this matter going around the black hole, very hot, and then the boundary of that material accretion disk. This is not the event horizon. So the event horizon is here. This boundary is called the innermost stable orbit for matter particles. So anything that matter, which means that anything that has mass, essentially, and not light, for example, but anything that has mass, electrons, protons, whatever, they can go around the black hole in circular orbits here, outside. But this is the last distance from the black hole that they can go around the circular orbit, and it is a stable orbit in the sense that it does not knock over into the black hole or outside, right? You can have this, but closer than this, any material particle that goes closer than this, then that material object will either, it's unstable, either go inside the black hole or go outside, and there's no way that it can go around this like a circle or an orbit, closed orbit around the black hole. So this innermost stable orbit is 3 times the Schwarzschild radius, 3 times the event horizon radius here. And this empty space is exactly because of that. So no matter can just stay here. It either falls into the black hole or goes up. You have this ring here, but actually it's a sphere, that is the innermost stable orbit for circular orbits of photons. Photons are particles of light. So although material particles that are not light, they have mass, cannot go further than this on a stable orbit, photons can do that. So photons can get closer and go around the black hole, which is very awkward because you see photons are really going very fast. So there's light. But then light bends so much that it goes around the black hole in a circle. But even light cannot get closer than that and not fall into the black hole, right? So if it goes a little bit closer, it cannot have a stable orbit. So it either falls into the black hole or goes outside, right? The situation is very different when you fall into the black hole. That's when you cannot go outside at all. But this is where you have a stable orbit for light. Okay, so they have this structure around the black hole, and now this is called the shadow of a black hole. So the shadow of the black hole that you see, this circle here, is this large circle here. Inside that circle, you have the photonosphere and you have the black hole itself. Okay. So you can see that here, something happened in my animation. This black hole should be at the center. Sorry for that. At the center of this photon sphere, and you see, if you look at the black hole from above, you see this picture. And if you go around the black hole slowly, you see this picture, which is very strange because that thing wasn't there on top of the black hole and bottom of the black hole. You had only this vertical, actually horizontal disk, this disk, right? But then again, you go around the black hole, and what happens is that, let's run it again. You see that you start from this picture. There's only a disk, and then you go a little bit. So you go with your satellite, something like that, go around the black hole, and this picture arises. So why is that? So why this happens? And that's actually the key is the curvature of a spacetime. So this is how this picture is is created. So look at here, this picture here on top left. Suppose that you are looking at the black hole from this angle, and this top and bottom are not real, these two regions, right? They are just, you really have just this disk here. This is the disk of material object rotating. Now, these lights, these yellow lights, for example, take this one from the back of the accretion disk. This actually, if there was no curvature of spacetime, this would go tangent like this. You couldn't see that. But because of the curvature of spacetime around the black hole, strong curvature, it goes and curves and bends and comes to your eyes. So another ray here and another ray. So this, what you see on top here, right? Here you see the yellow rays here correspond to the yellow rays here. The blue ones correspond to the blue ones, and the green here corresponds to the green. So from the back of the black hole, this ray comes up from the top of the black hole, hits your eye, and we perceive that as this thing that is on top of the black hole, which is actually nothing except the back of the accretion disk, except this, but you can see it also here. The same light from here, the same particle that emit light, that light also goes downwards, right? So some light goes up, some light goes down, and some, if there was no curvature, this light would go like this, and this would go like this, and you wouldn't see that. But again, the curvature of spacetime bends them, and again they come to your eye, and you see the same thing, the same back of the disk that you saw on top. You see the same back of the disk here on the bottom. So these two parts are exactly the same images, but kind of reversed, because one of them comes from the below, the other comes from the above. And in front of you, nothing bends. So basically, it's something, these lights come towards you, and this is the green part. So that's why you see this awkward picture instead of just seeing a disk here. Like the Saturn, if you look at the picture of Saturn, you just see the disk, right? The black hole is the same. Disk is around the black hole, but you see, because of the curvature of the black hole, is much stronger than Saturn, so you don't see that effect in Saturn or planets. These are other parts of the light. So the light also from the right comes towards you from the left, and from the back also turns around the black hole and comes towards you. So these parts are actually coming from the back of the black holes, really. And the same here. So this is how that picture is formed. And in order to show you actually better, let me show you this, all that I explained, let me show you in an animation. So this is the event horizon. And you see the lights, the curvature, the lights actually are bent and come towards you. So let's put the accretion disk around the black hole here. And the light from the left, okay, produces this picture. From back, they bend from the below of the black hole, and then again from the back, they bend from the above, from the top of the black hole, and you see all of these rays that come towards you, and they create actually this picture. But the reality is just a disk. But what we perceive is what you saw before, and this can be actually using computers, can be simulated, and you see this, which is very similar to the shadow of the black hole that was actually, the image that we got from the black. Okay, so there's something, because of that mechanism, there's something very, very strange also happening. So if you could actually see the shadow of the black hole inside, we cannot see anything inside the shadow, except the photosphere. But what happens is that this is the shadow, and this is the computations using physics and math. And this part here is actually the event horizon of the event horizon of the black hole, so the black hole itself. Now, because of the curvature of the space-time, what happens back of the event horizon, so the back of this sphere that you don't see, actually is mapped in this blue region, which is, as you can see it here. So that is the back of the event horizon. You can see actually that back of the event horizon. The whole event horizon, once again, is mapped in this part. You see this part? The whole event horizon is pictured here, which is very awkward because of the curvature. Once again, the whole event horizon is, one time more is mapped here, and this goes to infinity. Actually, infinite times. It becomes thinner and thinner, but it goes infinite time. The curvature of space-time kind of maps the whole event horizon all here. So this is what happens if we could see actually these, some structure on the event horizon. Okay, so this is about the exterior of the black hole. Let's get into the interior of the black hole. And here, Now, I want to give you a picture of a black hole, which is, so this picture is kind of a cartoonish representation of what happens of the geometry, space-time geometry of interior and exterior of the black hole. So it's not really this sphere is not really the black hole itself. It tells you a story of how objects move in a space and time inside and outside the black hole. So what I mean by that is that, so suppose that this is in the interior of the black hole, this is exterior of the black hole, and these lines, what do they mean? So the red lights that go upwards, those are the directions of time in the exterior of the black hole, outside. So everything must move forward in time. You can never go backward in time in the exterior, right? Even if you move left or right, you always have to go forward in time. So the left or right directions, these yellow vectors or arrows, these are the directions of spatial motion outside the black hole, right? So if you go left and right, these are your direction. But remember, you can never just stop in time and go left and right. You have to. This is a space-time diagram, not a space diagram. So in the meanwhile that you are going towards right, for example, here, at the same time you have to go up in time. So some time passes. You cannot just jump from one point to another point without any time passing. So then it means that when you're going to the right, you have to also go up. So your motion would be something like that, like something like this direction. And suppose that you now at this time you decide to go to the left. Again, you have to go like this. You cannot just go like this. You have to go, in a line with a slope. So an object that goes left and right in a space, so left and right in a space means that you are going in a space-time in this zigzag direction, in this zigzag pattern. So we have the same thing in the interior of the black hole. So we have direction of time and forward in time. So never, even in the interior of the black hole, you can never go backward in time. Never in the universe you can go backward in time. And these are the directions of spatial motion, left and right. But we don't have forward and backward because it's a two-dimensional picture. But you can think of this also as forward and backward. Again, if you want inside the black hole, you want to go left, you have to also go at the same time up in time or forward in time. So you go like this, and then left, right, left, right. And something interesting happens here because of the geometry of the space. First of all, this line that you see here, that's the event horizon, right? And if you pass this line, there's no returning back. And I will tell you why, because of its geometry. And the reason is that suppose that you enter the black hole and you always have to go forward, right? Here you can go outside, you can go forward here like this in all these directions. And there is no particular point in time or space that you end up. So you can go straight here or here or here or this point or this point. But here you see that every object that goes forward in time, even it goes in zigzag thing, always has to end up at one point, right? So there's no escape from going to that point. And when you go to that point, you cannot continue because you see all the time directions. These are all the positive time directions or forward time directions, even from the other side, right? So if you continue from this point this way or this way, it means that you're going backward in time. You cannot do that. So everything is stuck, gets stuck here at this point. And as you see, nothing can come out of this part, right? Because so if you continue here, if you want to come outside, either you have to go backward here in time or backward in time. So nothing can get outside. Once you enter this, there's no way to get out. Whereas if you take this small region here, right, this part here, like a square, if you can always get out of it, right? You can always get out of it anywhere you want. But this region here, you cannot get out of it. Every object ends up on that point, and that point is called the singularity. And that point, the singularity, which everything ends up and gets stuck there, we don't know what happens after that, but that is a place in time. Think about it as a place in time. It's a very dark comparison, but it's like death. It's always there in future of all of us, and you end up there anyway. But it's not some place in a space. So it's some place in time, and it's everywhere inside. So anywhere inside the black hole you are, at some point in time, you end up there. So that's a singularity. We don't know much about that in classical physics. We need quantum theory actually to learn about that. So as I mentioned, every object in the interior eventually ends up in that. And to give you a better geometric picture, or maybe another geometric picture of that, is that take the black hole, the event horizon, and the singularity. What happens mathematically? Really, it happens in mathematics. You have direction forward in space and backward in space outside. This is like the right and left that I showed you in the previous picture. Now, something like a magic, not really magic, but science, but anyway, so something like magic happens, and directions of a space and time kind of switch in the sense that now you have forward in space and backward in space, the same directions that were forward in space and backward in space, now in the interior become forward in time and backward in time. So if you want to go backward, really, in what you thought is the direction of backward in space, in the interior actually it's the backward in time. That's why you can never go back outside of the black hole, because going out of the black hole means going backward in time. Nothing can do that. So you always end up in the singularity. But is there any hope to get out of the black hole? Yes. The hope is actually coming from quantum gravity. So first of all, if you look at this point actually ends all the directions, ends all the curves that you see here. So none of the curves outside are ended anywhere, but all of the curves end here at this point inside. So this we call this point the end of space-time. So space-time is not continued after this. Everything is stuck in here, and there's no other curves that continue from here. And as I mentioned, this singularity, as in the beginning, I said that this is infinite curvature. So this is the prediction. Anything that in physics you get to an infinity, it means that this is not a number, and it tells you, it signals the end of that theory. That's beyond the prediction of the theory. And it is a prediction of general relativity, but it's beyond the domain of it, because the general relativity is telling you that, okay, at this point I cannot tell you anything. Everything becomes infinite. So notice that singularity is not only an extremely high curvature region in space and time, but it's a very small region. And whenever you have a very small region in the universe, small things, you have to apply quantum theory. So extremely high curvature, or very, not extremely, even high curvature regimes, when close to massive objects and all those things, you always need the theory of gravity, Einstein's general relativity, to explain things. You cannot just do Newtonian gravity, right? It's not very correct. But when you have a very small region, you need quantum theory. There are very few places in the universe that are at the same time having very high curvature and are very small in length. And one of those regions is the singularity. And because of that, we need these two together to be able to explain physics here. Gravity itself cannot explain here, and not quantum theory itself. So the combination of these two theories is called the theory of quantum gravity. And that is the hope that if we have that theory, we can find a way out of this problem here, the singularity. Let me tell you actually what quantum gravity usually, we don't have the full theory of quantum gravity at all yet, but we have bits and pieces. We have a string theory, we have loop quantum gravity, that is my area of work, loop quantum gravity. And we have other types of quantum gravity theories, but none of them have the full answer. Some of them have some parts of the answer. Most of them, that's a prediction. What they do is that, okay, so this is my black hole representation of the black hole space-time. And quantum gravity actually can remove that singularity. What does it do? It actually represents, so if I go back, so it takes this point and actually changes that. It shows us actually something in the space-time changes because of the quantum theory. And these curves that you saw end up at one point now don't end up at that point. So they now can be continued to some other region. So a new part of space-time is kind of created. And at the other part of the space-time that you see here, another copy of this black hole exists, but now that is actually the inverse of this black hole, what the physicists call time reversal of a black hole, and that is called a white hole. So what you see here, these are the directions of time outside. So you can just continue outside. If you're outside the black hole, everything is fine. You can just go forward in time. But inside, these were the directions of time, right? So always you have to go forward in time, even if you go back and left and right. So you go here, instead of ending up at this point, now you're free to move forward in time, and then you go back here. And you see inside the black hole, there's no way that there's no escaping outside, right? Everything is just kind of attracted towards this part. And the reverse of that happens in the white hole. You can never stay inside the white hole, or you can not get to this region from the white hole. You're spat out. So everything is going out of the white hole. So that's why in that meaning, in that sense, the black hole is in a time reversal of a white hole. You see the direction of time actually is backwards here, right? So the direction of time is towards this blue region here, the black hole, but the direction of forward in time is now the other way, away from the black region. So everything should go out. There's no way you cannot stay here. And that's another event horizon, and everything comes out. So this region that is in the center is called the wormhole. And that region that I mentioned is called the white hole. And you see everything about this is about the space-time, is about the gravity, right? The space and time are actually look very innocent subjects and concepts, but they're really extremely mysterious and complicated. We don't really still know what they are. But anyway, so this is the conceptual representation of what quantum gravity does. And let me give you a few more kind of visual representation of what happens. So let's say we want to fall into a black hole. Now, remember I told you about the innermost stable orbit for material objects. So this is the circle that around the black hole you can go as an object with mass and stay there and not fall into the black hole. So if you are there, this is what you see. So these are the stars. This black circle here is the black hole. You're outside of the black hole, so you look around and you see this around you. So the universe outside is extremely, these things are kind of curved because of this effect of curved space-time. And here, objects go to the right, here seem to go on the left. These are all illusions, basically. These are our perception because of the curvature of space-time. So you look around and you see this. Remember that you are now going around the circle around the black hole, right? The stable circle. Okay, so this is the innermost stable circle orbit. Let's go a little bit further. Suppose that you are a photon, you're a light ray. We cannot do that, but if you're a light ray, now let's get closer to the black hole. 1.5 Schwarzschild radius, or 1.5 times the radius of the black hole. So now again, you're going on a sphere or a circle around the black hole, but you're way closer to the black hole. You can look around if you're a photon, and you see almost the same thing. The space outside. Now, you notice that the space outside looks blue, bluish, and there's a reason for that. And the reason is that the light rays that are coming towards you from outside are getting more and more energy from the black hole, becoming energetic. That's called the blue shift. The inverse is true. If you're outside of the black hole, the light's coming from objects close to the black hole to you outside, they become reddish. That's called the red shift. So you see the blue shift here. The universe outside looks kind of a little bit awkward. You see the rotation, and you go faster and faster. Things become, you see that it's rotating. We are rotating now faster, and things become really dizzying. So I'm going to stop the video now because it really becomes really dizzying. So, and the next video is actually the falling into a black hole. So if you fall into the black hole, this happens. So this is the black hole in the center. Now we are getting closer to the black hole, and you see the effects of the lensing around the black hole, the curvature. You're falling inside, and we want to go, look from when we are falling. We want to look outside. So the things are becoming bluish and bluish, more bluish, and the whole universe is now kind of condensed into one circle, and kind of disappears as a point. But because all of you are really great audience, now I'm going to return you back. It's not physically possible, but let's rotate back. So if you want to return back from now we were inside the black hole, but we want to return back. So gradually we get out. And this is the picture of the experience of a white hole. So you get back, you can come out of the black hole, and you can go back and look at the black hole from far, and we could actually get out of the black hole. Another last thing actually I'm going to mention is the fact that not only space is curved, but time also is curved inside the black hole, and the perception of curvature of time is that things, when time is more curved, it passes more slower. You can think of it like that. So when you're close to a black hole, time passes for you slower than objects outside. And when you get closer and closer to a black hole, objects outside seem to run faster and faster. So this is actually what happens. So you see the universe, you're falling to the black hole. Things are kind of moving normal, but the outside universe seems to go faster and faster. You see that sphere of the whole universe. You see things are really going fast. You can see really, into the future. For objects outside, each second for you in the inside or very close to the black hole is maybe 100,000 years or even faster, or for 1 second for you is 100,000 years for the outside. So you see, in one blink, you see the whole history of human beings, 100,000 years, and then you go further and further, and so that's a good way to imagine this. And let me just give you the last slide, and that last slide is, we have supermassive black holes. You have all sorts of black holes, but we have supermassive black holes usually at the center of the galaxies. And you see, this is our solar system, and this is the orbit of Pluto, right? So this is very, very large for us. But then the black hole itself is way larger than that. You see, it's like maybe like 37 times the Pluto's orbit. So if you fall into this black hole, you can just imagine, nothing happens really to you, because if you want to reach the singularity, it takes the age of the universe, because it's very, very far away from us. Far away, the singularity is far away from you. And the mass of this is almost 1/3 of the mass of the whole galaxy. It's very large. The lifetime of this black hole, so the black holes actually disappear because of the quantum effects, but the time it takes for them to disappear, you see, it's 10 to the power 88 times the age of the universe, which means that basically put one with 88 zeros in front of it, that much times the whole age of the universe, which was 13 billion years. So these are really the giant objects that basically are much, live longer, much more than the whole universe. So I will stop here, and I'm happy to answer any questions.
Thank you so much, Saeed, for sharing this incredible peek into black holes. We are going to go check in now with our Rastgoo DDO outreach coordinator, Quentin Wayrich, who has been monitoring the YouTube chat for questions from our viewers. Quentin, over to you.
Hello, Professor Rastgoo. Thank you for coming on tonight. We have quite a few really interesting questions from the YouTube chat, so I'm going to share those with you now. First of all, from Obsidious, why does a mass cause space-time to curve? If gravity is the curve, what causes the curve? Is it electromagnetic attraction, nuclear attraction? What makes the space-time curve?
Right, that's a very good question. So the short answer is energy. Anything that has energy curves the space-time, whether it has mass or not, because we know from Einstein's relation, we all know E equals mc squared. So either the objects have mass, they have some energy, of course, because of this relation, or even they don't have mass. Anything that exists has energy, like light. That's why when you have a strong ray of light, you get, it heats up the room and everything. So because they have energy. So anything that has energy curves the space-time. And why anything that energy curves the space-time? These are one of those questions that really physics cannot answer. It's like asking why anything that has a negative charge attracts a positive charge. We really don't know. That's how universe works. We just discovered these relations in the universe.
Okay, from the same asker, do black holes attract each other? If so, what happens when they merge?
That's also another great question. Of course, actually, gravity is the most universal force. Everything attracts everything. Everything that has energy attracts everything. And the reason is that anything that has energy curves the space-time, and any other thing close to that curvature kind of falls into that curvature or is affected by that curvature. So, of course, black holes also attract each other. And if they merge, a new black hole is formed. And that is actually what we can hear by gravitational waves. So gravitational waves are perturbations of space-time. So if you perturb water on in your pool, you can see the waves propagating. The same thing happens if you perturb the space-time. Space-time, think of it like an elastic band or a elastic sheet that I showed you. So these perturbations can propagate on that like water waves, and we can hear them or actually see them, what you can call it hearing or seeing, using the gravitational wave observatories. And actually, the way we can see them or observe them is that we have lasers between 2 points, and these lasers actually, simply you can think of the ruler. We have a ruler that measures the distance between two specific points, and actually when the gravitational waves comes in, changes and oscillates the distance between, makes it smaller and larger and smaller and larger, the distance between these two points, and we can observe them in our observatories. So that's actually what happens physically. Two black holes, when they're going around each other, make perturbations in the space-time, but then they merge to each other and become one black hole, and everything goes quiet.
And that was what LIGO made headlines for detecting a little while ago, right? The
Exactly.
Gravitational waves? Excellent.
Exactly, yes.
That's fascinating. Again, from the same asker, we have a question. If photons cannot escape the black hole, how are we able to observe the rays from the black hole to apply mathematical concepts to understand what we see from curved time? Is it theoretical versus observed?
No, photons cannot or anything cannot escape from the interior of the black hole. But it doesn't mean they cannot escape from the exterior. Anything that is in the exterior of the black hole, exterior of the event horizon, not the shadow, even inside the shadow, but not in the interior of the black hole, anything can, in principle, escape. Well, it depends on their energy, right? If their energy is high enough, they can have enough speed and they can get away from the black hole. But once they reach the event horizon and fall into the event horizon, nothing can pass. So the lights we see are coming from the exterior of the black hole.
Excellent. Okay, a question from Gordbo. Are there any predictions for quantum gravity that have been observed or that are being looked for?
Right. So there are a few things that there are many things that we are looking for, especially in the early cosmology and and black holes. Unfortunately, we don't have access to the interior of the black hole, so we have to find something. Most of the, I would say, not evidence, but the reason we kind of believe that quantum gravity should be there and we have to find it is that we believe that the universe should and can be explained by science, by physics and math. So when we reach some place that we like the singularity, that something goes awry, so that doesn't work, it means that there should be another theory that works that we can explain it with. That's why people are looking for quantum gravity. But the specific things that people are looking for in experiments, one of them is, for example, when you look at the very high energetic photons that coming from far away objects, or even the gravitational waves, one of the signatures of quantum gravity can be that the propagation of the wave, the speed of the waves, depends on their color. So the blue colored photons, or high, basically the wavelength, actually, lower wavelength ones should come slower compared to the ones that have higher wavelength. So that's one of the experimental evidence we are looking for. There are other evidences that people are looking for, but we don't have a smoking gun yet for quantum gravity, unfortunately.
I see. So loop quantum gravity predicts the existence of white holes. Are there active surveys going on looking for evidence of white holes?
Yes. So this is part of many of these, the observatories in space or on Earth. So some of their time is actually surveying, for gamma ray objects, for objects that emit really high energy, photons or light, and those are candidates for white holes. But we don't know yet if they are white holes or not. It may well be the case that the black holes are so long-lived that at this age of the universe, none of them still disappear. Because really, in the for the observer that is inside the black hole or falling to the black hole, everything may happen in 5 minutes or 10 minutes. But because of the curvature of time, because of strong gravity, that 5 minutes for them maybe they're like 5 times the age of the universe for us.
I see. I have a question here from Jonathan Chu. Why is it important to study black holes? Any application we may see in daily technology?
That's a good question. So on the theoretical side, I would say that black holes are maybe the most interesting objects in the universe because they have everything. They are related to quantum gravity. They're related to gravitational waves. They're related to some other effects related to the cosmology, because interior of the black holes actually looks like a cosmological model mathematically. But apart from that, for technology, think about. I will tell you what technological things we can actually get from them. But imagine the beginning of quantum theory, right? Like 100 years ago, Einstein and Bohr and others were talking about completely, theoretical things. What electrons are here or there or something like that, and none of them was thinking about, the technological advances or technological things that we can get out of this. But it turns out that every important fundamental physics discovery that we have had or before always future has led to significant technological advances that we have even never thought about. Because think about all the computers we have now, supercomputers, medical imaging, everything that you have here, even the GPS that you use everyday life. So those were all the results. GPS is the result of general relativity, but every other thing that you see is the result of quantum theory that we never thought at that point. Imagine a cell phone, talking about to Einstein about a cell phone. They just don't believe that. For black holes, we already know some of the applications. Suppose we have some simple model of you can actually you have your things that you want to throw away, and you can just throw them inside the black hole, and there's a way to throw them inside the black hole and get energy out of that. So you get free energy, and you also dump your anything that you want to throw out, and that's one of the applications.
Free energy from garbage. That'd be excellent.
Exactly.
So Obsidious says, first of all, thank you, Dr. Rastgoo, so much for being able to explain complex questions in layman's analogies. Awesome help in understanding. And then follows up with a question. If looking at a white hole, would the human eye see something like what appears like a supernova?
So just looking at the black hole, right? Not a...
No, looking at a white hole. What would a white hole
okay,
like to
yes.
the human eye?
Yes, exactly. So we probably would see something that is emitting really high energy particles or photons all the time. Might look like a star, but very, very shiny star. I'm not an astrophysicist, so I'm not the best person to ask about that. They're more theoretical physicists. But I imagine that from the models that we have, that would be something that we see. But really high energy objects, so something that really shines as the whole galaxy, like 100 billion stars.
Okay, I know that there are supernovae that have been comparable in size to the brightness of their entire galaxy. So perhaps we'd see something like that, but of course it wouldn't be limited by any stretch of time. I imagine it would just be like a constant glow.
Exactly. So if the models are correct, so depends on the model, but some of the models actually predict that would be a flash of light, maybe 1 or 2 days, and that the whole white hole disappears.
Oh.
But there are other models that tell you that it's lasts much larger time. We don't know yet. They may not even exist at all. So there will be other mechanisms. I remember that I mentioned that quantum gravity models or theories, not all of those parts are correct or can explain things in the best way. So the white hole thing, some of the quantum gravity models explain, predict that, string theory, loop quantum gravity, but we can actually modify these theories to not predict those things. We have to kind of do some gymnastics, mental gymnastics. We shouldn't, but even if so something here is actually interesting to mention, that even if we don't see white holes, and even if that leads to the refutation of a theory being loop quantum gravity or string theory, we as scientists at the bottom of our hearts would be very happy. Of course, for our jobs would not be happy, but for the science we would be very happy, because that's one of the main reasons we do science, to just refute things, diagnostics, and get the best theory there.
Certainly, even a null result tells us something.
Exactly.
I have a question from Denise, actually. Perhaps it is a trivial question, but is it theoretically possible that our universe could be inside a massive black hole? How would it be possible to know?
Right, that's definitely possible, and that's something very interesting. We could be in a very large black hole. Actually, there are so many theories about our universe. You can be in a simulation, you can be in a black hole, you can all of those things. But in order to know that, I would say that we have to travel. Well, we will hit the singularity at some point if that's if you are in the inside the black hole. But we probably could do some really precise measurements about the trajectory of object going around, and probably see that. So, for example, we know that inside of a Schwarzschild black hole is a special type of black hole that has mass but doesn't rotate and doesn't have any charge. We know that in the interior, there's a universe that we call Kantowski-Sachs, which is different from the universe that we are observing now. Our universe is called FLRW, Friedman, Lumet, Robertson, Walker. This is a model. So our universe is this and not Kantowski-Sachs. So it tells us that we are definitely not inside the Schwarzschild black hole.
Okay, that's really interesting. I appreciate that it is actually possible to know if we are in a black hole, that it's possible to narrow down what kind of black hole it is. It seems like the kind of question that it'd be no way to answer, and I think it speaks to the power of science that we are able to give some definitive answers to that question.
Definitely, yeah, exactly.
I have another question from Obsidious. Do you think it would be possible to pass through a wormhole? Would we have to be in the form of pure energy without mass to do so?
Yes, so it depends on the model and everything. So, but for loop quantum gravity, at least some of the models of loop quantum gravity, it is really not possible to. Remember the slide that I mentioned? It's like a highly quantum regime, highly quantum area. It means that that area you cannot even assign to it a space-time picture, because a space and time, if you think about them, space-time, many physicists believe that the space-time itself is an emergent phenomenon. This is our perception. Think about what I'm talking about, the emergence. So think about a gas, right? A gas, if you are a molecule, you see the gas as a bunch of molecules going around. You don't see anything continuous or anything that has a volume or temperature. Temperature and volume and pressure don't make sense when you're on the level of molecules. But when you see lots of molecules from far away, actually you don't see the molecules anymore. You see like a fluid or a gas, and you can assign to it pressure and volume. So these pressure and volume and temperature properties, these emerge. They don't exist. They don't make sense on the level of molecules. The same thing physicists think, that if you go really on high quantum scales, really small scales, or high energies, space and time don't lose their meaning. There's no space and time. So there is something on the background. We don't know what it is. That's one of the jobs of theory of quantum gravity to explain that. But there's something there that if you look at it from far away, that looks like a space, continuous, smooth space and time. So that's what we mean by emergence. And if that's the case, the highly quantum regime at the wormhole, if it's highly quantum, then it doesn't make sense actually to assign to it a notion of space and time. Things can move around in some way. You can go from black hole to white hole, but that's another, other conceptual things that, you cannot assign them to space and time. So bottom line, in this form that we are, we can probably not pass the wormhole.
Okay. It seems like it's very dependent on like the specific framework of the theory being considered. That makes
exactly
sense.
Yes.
I have a question from Grace Horvaten. How is it possible for a black hole to be older than the universe? I believe this question is in reference to the lifetime of that supermassive black hole that you showed us.
Exactly. So what I mentioned, maybe I didn't mention it very clearly. So I mentioned that the lifetime of a black hole is or can be larger than the present life of the universe. So I didn't mean that the black hole now that you see in the universe is older than the universe itself. It means that if you take a black hole that was created 2 days ago and measure the mass of the black hole, you can predict how it or when it disappears. And that time that is in the future would be larger than the current age of the universe. So that's what I meant. Maybe hopefully it's clear.
So you'd be waiting for a very long time. Wouldn't really be worthwhile to carry out an experiment like that. On a more personal note, I have a question. What got you interested in astronomy in the first place?
Right. So so it might be something that many people say, but this is true in my case. So when I was a kid, I remember my mom always liked and still likes to be an astronaut. So she bought astronomy books for me out of her curiosity. I remember some of those books were about I remember actually clearly one of them was about black holes, maybe 10 pages with pictures and everything. So for kids, I think I was like maybe 6 or 7 years old, started knowing how to read and all those things. So all these, astronomy books made me really interested in black holes. Then when I was in high school, I created a group, and also in first years of my bachelor degree, I created a group. We actually constructed telescopes, the whole thing with the mirror and everything using the Newton's method, and we observed Saturn and everything with those really nice times and exciting times. So gradually, I learned about other things, got gravity and the cosmology in more detail, and I got more attracted towards the theoretical part of it, the gravity and quantum gravity.
I wonder how many astronomers and physicists first get into the topic just from reading stuff when they were kids, because I know that that's my background too. That's what got me interested in physics. I did a lot of reading when I was a kid.
I think that happens to many of the scientists like you. Yes.
Another question I've got, is it true that there is a black hole at the center of our galaxy?
Yes, definitely. That's proven beyond any reasonable doubt. So, at the center of not only our galaxy, at the center of all the galaxies, or most of the galaxies that we see in the universe, there is a supermassive black hole, very large. And actually, there are these objects called quasars that actually they're theorized that they are the black holes at the center of very old galaxies that are spitting out gas and matter. But yes, at the center of our galaxy is actually not a very large black hole compared to other supermassive black holes. So there are black holes that have other galaxies that have like black holes 1,000, 10,000, 1,000,000 times larger than our black hole.
Wow. Okay, that's fascinating. Or the majority of galaxies have a supermassive black hole at their center. That's kind of crazy to think about. Okay, yeah. I've heard of quasars. I didn't realize that was what caused them.
Yes, as far as I know, those are the models that we have. Again, so I'm not an astrophysicist, but I think as far as I know, that's the case.
All right. Well, thank you very much, Dr. Rastgoo. I believe that concludes all of the questions that we have for tonight. Thank you very much for coming on.
Thank you very much for having me.
Thank you, Quentin, for relaying all of those great questions from our audience. What a dynamic question period that was. That was wonderful. And of course, a special thank you to Dr. Rastgoo for answering all of those questions in so much detail. We've all learned quite a lot tonight.